Alright, welcome back. In this we're going to go over hydrohalogenation with chirality practice problems. I made a lifetime total of $169, nice, and 1 cent. If you have not watched my last organic chemistry video on hydrohalogenation mechanism with Markovnikov, anti-Markovnikov, please watch it because this is like the second tier video. This is like the next level of this. So you need to learn how to drive before you drive. I don't know, that's okay, whatever. The hydrohalogenation mechanism can make chiral centers. So when you do the mechanism, there's a chance your product will have a chiral center. You are making a chiral center. If it does not make a, if it does make a chiral center, 99% of the time it will be racemic. This means you get the wedge conformation and then you get the dash conformation. This means you need to put both versions on your exams. Students always tend to mess this up. Here's what they do. You do the mechanism and you put the product, your halogen that you just added, on a normal bond line when it's supposed to be chiral. This is immediately, you got the problem wrong. That's incorrect. And you're going to get points off. The second mistake that students do is they just put the wedge configuration. They don't put the dash, or vice versa. They put the dash, but they don't put the wedge. You need to put both, because both are answers. And professors know this. This is why your professor is testing you on this. He or she is giving you this on an exam, knowing that you may mess up. They're seeing if you know what you've actually learned. And I want to tell you why you get a racemic mixture. This is the hydrohalogenation mechanism. I went over the entire thing in my last video, so I'm going to go over it very briefly here about why you get a racemic mixture. After the proton transfer step, we are left with a carbocation. This carbocation is trigonal planar. It's basically flat. Since it is flat, when the nucleophile comes and attacks, it can either attack from the front side or the back side of this electrophile. And that is why you get a wedge and a dash. There's a 50-50 chance it'll happen to either. Either it'll attack on the front or it'll attack on the back. And that's why there's a 50-50 shot you're going to get a wedge or a dash. And that's why you put both on an exam. That's that simple. It's because of the geometry. Okay, let's do some practice problems. Predict the products of each reaction. Some may produce a chiral center, some will not. Okay. We have our alkene here. We have HBr. We do not have peroxide, so we're going to be doing a regular Markovnikov addition. This means the bromine will go on the more substituted carbon of the alkene. This carbon is more substituted than this one, so we're going to expect the bromine to be here. Here is the trick on basically checking if it's chiral. On your starting molecule, draw bromine, whatever halogen is listed here. Now look at the carbon that you just added it to. Are all four groups different? This is different from this, and this is different from, they're all different, okay? They're all different. All four groups are different. This means we do have a chiral center, and we're going to get a racemic mixture of wedges and dashes, meaning you must list both enantiomers. Like that. So the bromine is on a wedge here, and bromine's on a dash here, and vice versa. You must make sure you put the other group that's here, the side group here, that's not part of the actual carbon chain, on a wedge or a dash. People like to forget this. What they do is they just put the bromine, and they just leave the other one. You cannot leave the other one. You must, whenever you do these kind of problems, make sure you always have a wedge and a dash. Okay, let's do B. B, we do have a hydrochloric acid here. No peroxide, so we're going to be doing a Markovnikov addition. We look at the alkene, and we look at which carbon of the alkene is more substituted. This one's more substituted than this one, because it has more branches. So we're going to be looking to add the chlorine here. So if you do this, you erase this, because that's what the mechanism is. We get rid of the double bond to attack this. we get chlorine. The question is this chiral? The answer is no. Not all 4 groups are different. This group right here is the exact same as this. So it is not chiral. We will not have enantiomers. You will leave it as it is, like this. That would be the answer. Now, the trick to doing this is, imagine you have your starting molecule. Get rid of the double bond. Is this symmetrical? If your molecule is symmetrical, you will not have a chiral center. That's the trick. Okay. There we go. Let's do C. This one is a trick question. Be very careful. We have HBr, no peroxide. So we're going to be doing Markovnikov. They're all Markovnikov. I'm just going to tell you that, as you can see. We're going to be looking at the more substituted carbon of the alkene. This is more, oh my god. This is more substituted than this. So we're looking to add the bromine here. Something like that. We could be careful now. How do we draw this? First question is this chiral? A lot of people have struggles with identifying, is the compound in interest chiral when you have a ring? Here is the trick to doing so. When you want to find out what carbon, if your carbon of interest is chiral, so just first mark the carbon of interest and work clockwise and counterclockwise. What we're going to be doing is comparing the carbons. Are they the same or are they different? If they are different, then there will be chiral. Then what you're looking at is chiral. For example, we start here. We notice that this carbon right here has 1 branch, 2 branches, and rest of the ring, which we don't count. So it has 2 branches, 1 and 2. If we compare this carbon with the very next carbon going counterclockwise, or clockwise, rather, sorry, going this way, so this one, we notice has no branches. So we can immediately stop. Since they are different, this is going to be chiral. This is assuming the other groups are different, which it is, right? Because you're adding a bromine here, and then this is not a bromine whatsoever, so it's going to be chiral. That's the trick. Okay. We add the bromine here, right? For example. But we have to make this a dash or a wedge, right? So just say we make the bromine a wedge. This means this has to be a dash, okay? Here's what you do. This itself, if it comes off a ring like this is going to be your dash. And then this is where you're going to connect it with the dash with. Okay? Because you got to think that this is coming out of the ring. It's coming out of the ring, meaning we're not adding an additional bond here, if that makes sense. We're connecting the ring and bromine together with a bond, because that's what the mechanism is. But when we just transition something that's already on the molecule to a wedge or a dash, you just replace what's over there, the first bond, with a dash or a wedge. Because if we were to do this, pretend that we do this. This is saying there's a 1 bond here, another one, and another one. There's 3. There's not an extra carbon there. This would be adding an extra carbon, right? Because this is a carbon right here. This would be 1, this would be 1, and this would be 1. So, not counting the one on the ring, we have 1 carbon here, 2 carbons here, 3 here. But look at our original molecule. We only have 1 carbon and 2 carbons. This is why you have to be careful when you do these stuff. What people like to do is they like to just copy and paste this and add a dash or a wedge connected to the ring. You cannot do this. You have to be careful. That is why you will get this answer. It looks funny, I know it looks funny, but this is the correct answer. in nantimeters. Okay, let's do this one, the bottom one. Is this chiral or not chiral? Well, if you were to add the iodine, just say we add the iodine here. Pretend. Okay, this is different from this one. That's fine. Now we have a ring, so we have to do the carbon check, the carbon ring check. We go up. This carbon is the same as this one. They both have one, no branches coming off it. It's just part of the ring. That's fine. We don't count this alkene there. Just pretend it's not there. So this is the same thing as this one. Then we go up one. This one is not the same as this one because this has 2 branches coming off of it, and this one doesn't. So they are not similar. So it's chiral. Our product will be chiral. Okay, we have to look at what carbon is the most substituted. This is more substituted than this because we have an extra branch coming off of this one. This one has no branches coming off of it. So the iodine is going to go here. I kind of revealed that already, but yes. So we're going to be left like this. And see, this is the same thing I was talking about. This is this. Right? So whenever there's something already on the molecule, we're not adding anything. We just got to change it to wedges or dashes. Just change the first thing that's connected to a wedge or a dash, and then you're going to get your answer. And that's it. If you found this video helpful, please like and subscribe. Until next time, later.